The first one I wanted to do because this question comes up a lot. You're probably going to see a question like this definitely on your exam, and I'm sure there's questions on the final too. And I'm getting a lot of net ionic questions, so we'll go over a few of those net ionic questions also. Okay, so, and I don't know if I'm going to be able to get up to all of them today, but I'm sure I'm going to try. All right, so let's see here. Okay, so for this question is using the solubility table again and again and again and again. Let me just see something really quick. I'm putting the solubility table on this one because I don't want to look at it like 1,000 times. Okay, there, now we can see our solubility table. All right, so this question is actually kind of a common question, and it's using the solubility table, which I think will really help. And again, in Chem 101, we have an expanded solubility table, but for your exams and quizzes, we're going to be using this little mini abbreviated one. So again, all for your exams and your quizzes, this is a solubility table you'll be referring to. Just know it's an abbreviated version of a solubility table. So I actually grabbed one from Chem 101 that used a bigger one just so you could see it. So this question, I know you can't see it very well. It says, which one of the following would form a precipitate when mixed with LiOH? So remember, precipitate means solid, right, or insoluble. So when we do this, what it's asking for us to say, does LiOH make a precipitate with KNO3? Does LiOH make a precipitate with NH4Cl? I'm only going to do one more. We're just going to not do these two, okay? Because it takes too long, and we'll get to the answer. C3H2O2, 2. I'm going to put LiOH just to keep it similar. C2H3O2, 2. Okay, so we're only going to use this solubility table, not the expanded one. All right, so these are just real quick double displacement reactions. So when you see a question like this, don't balance it, don't do anything, just put down the products, because all we're trying to see is which one of these is going to be insoluble, right? So Li stays first and K stays first, and the other two switch. So LiNO3 and KOH. All right, well, I know that all nitrates are soluble. That's not a solid. Go to our hydroxides down here. All hydroxides are insoluble except ammonium and, oh, alkali metals. That's group 1. That's an alkali metal. This means it's soluble. Not our answer. Your next one, Li stays first and NH4 stays first. The other two switch, LiOH, NH4Cl. Okay, let's look at our OHs here. Again, this is an alkali metal right here. So it is soluble. All ammonium salts are soluble. That's soluble. That's one's not our answer. All right, let's go to the next one. Li stays first. Ca stays first. Acetate goes here. OH goes here. And again, I'm not even balancing them because it's only asking me like which one makes a solid. So I'm not going to waste my time balancing it. So I know that right here, all acetates are soluble. Not my answer. Let's look at this one. Hydroxides are insoluble except ammonium, not ammonium, and alkali metal, not alkali metal. So therefore this is our solid. So that, for using this solubility table, would be our answer. Right? And so you will see questions like this, and yeah, they're really long. They're long questions because you kind of have to go through each one. And there might be a shorter way to do it, but I don't know of a shorter way to do it. I just go through all of them. Okay. Let's look at the next one. And at any time, if you have questions on these, please just interrupt me at any time and we'll go through them, or I'll answer your questions.
I have a question.
It says that that's incorrect on Chem 101.
What?
It says that answer is incorrect on Chem 101.
Yeah, so that's why I was saying I wasn't doing the Chem 101. I was just using our solubility table, because if you use the Chem 101 solubility table, it's bigger and its exceptions aren't the same, right? So for example, on Chem 101, insoluble hydroxides are these, and these are soluble. So if you're using the Chem 101, on Chem 101, this one does say it's soluble, but I want you to see how to use this using our solubility table. Yeah, so that's why I didn't do this one. That's why I stopped here, because I just wanted to show you it on our solubility table. It's a Chem 101 problem, but I was just trying to show you on ours, because again, this is the abbreviated solubility table. This is the Chem 101 expanded solubility table. So for your exams and quizzes, we'll be using the smaller table. Yes.
Is it supposed to show their insoluble table on the problem? Because it doesn't.
It shows you if you get it wrong the first time. So if you get it wrong the first time, it pops it up.
Oh, okay.
Yeah.
So
if you get
not C?
I'm sorry, what was that?
It's not C then? It's wrong on the.
Yeah, this is not the answer for Chem 101. This is, don't choose this as a Chem 101 problem. I'm just using the Chem 101 problem as an example. This is not the answer from Chem 101, because on Chem 101, you're not going to use this table. You're going to use this table right here. That's on Chem 101. And if you click on Chem 101 on the little pluses, the solubility table will pop up. That's where I got this. I popped it up from Chem 101 to show you this. Okay, and we can come and do another question like this also with these, but let's use our solubility table. And again, the reason we're using the small one is because all of the chemistry faculty before I even got here said, let's use this baby solubility table, but it's very limiting to the number of questions we can do. That's why most places Chem 101 uses a much bigger solubility table. But for your exams and quizzes, again, you will only be responsible for using this table right here. Okay.
So the reason, sorry, I just have a question. A reason why we might be getting it wrong is because we're using our solubility table and we should be using the one on there.
Yeah, if it's not working on your solubility table, that might be it. I've only had 2 questions that was the case.
Oh, okay.
This is one of them that we just did, which we can come back to it. And then this one right here. The rest of them, the solubility table works fine. And the perchlorate question.
So
but all the rest of them work.
In order to get to it, though, you have to get it incorrect on one, so you're just wasting one of your turns.
No, you can hit the little plus button and it'll bring you right to it.
Oh, okay.
Yeah, there's a little button you can, that's how I got to it. I just hit the little plus button and it brought me right to the solubility table. Yeah, it's just like a little extra button you have to push on the side. Okay, so let's try this question because I got this one a few times. So complete the balanced molecular equation. That's our regular plain Jane follow these steps equations, right? Complete ionic and net ionic, that's a different piece, right? That's extra. Again, this is a double replacement, so I just put this on here for us. So when we write our products, Cu stays first and Na stays first, and then we flip our polyatomic ions. So PO4 goes here and SO4 goes here. Now we still have to balance our charges, which I didn't really leave enough room, so I'm going to put this down here. +2. Oh, that's not a +2. This is a, I can write -2, +1, +1, -3. So this one must be a +1, so a -3, +1, -2. So I have to put a 3 here to balance it out. And there you are, my charges are balanced. Now this one asked for a balanced equation, so we have to balance this one. For our states, again, we'll look here, or we can use the Chem 101 solubility table. It works the same. I personally kind of like theirs a little bit better. But when we look at this one, our sulfates, sulfates.
Doesn't it equal Na2SO4?
Thank you. Yeah, I forgot the 2. all sulfates are soluble except for barium, strontium, or lead. Well, this is neither barium, strontium, or lead, so yes, this is soluble. All right, phosphates. Phosphates are insoluble except for ammonium and alkali metals. Well, this is not ammonium nor an alkali metal, so this is a solid. So this is our phases or our states. Then we have to balance it. And again, however you want to balance it is fine. For this one, if you just want to balance it quickly, I can see that this is a 3 coppers and 2 coppers. Well, no matter what, I need them to be the same. So if I just make them both be 6s, then at least I know my coppers are right. You can do this the long way also, but we have a lot of questions today. I want to make sure I get to them. And when we do this, again, our coppers are working, but look at our NAs, 3 NAs and 2 NAs. If I can make them both be 6s, I can get it to work. Maybe. It's just like a little trick that you learn after a while. So we check 6 CUs, 6 CUs, 3 SO4s, 3 SO4s, 6 NAs, 6 NAs, 2 PO4s, 2 PO4s, balanced. Okay, so this was a question. Does anyone have any questions on this one? No, we're good on these. It looks like a lot of the questions are complete and net ionic ones. This is one I thought was a great question. So for this one's a single displacement, right? Because it's 1 compound and 2. So again, our question is, can tin kick out silver? And we have to use our activity series, which I didn't have time to copy. So we have tin and silver nitrate. So I have to go all the way back here, sorry. Here we are. C activity series. So it's tin plus silver nitrate. So tin has to be stronger. So can tin kick out silver? So if we look here, here's silver and here's tin. So tin is stronger. So tin can kick out silver. So this reaction will occur. So when we do this, then we get silver all on its lonesome, and then tin is going to be with nitrate. But again, on this one, this is going to be solid here, and this will be AQ. And so when we do this one, tin's charge is either a +2 or a +4. So I'm just going to say it's +2 because it'll make my life easier. SN2. And then we have to balance it. And it's balanced. So this is a single displacement reaction. And again, with those, we have to make sure that we check out the activity series to make sure, that whichever one we want to kick out has to be on the stronger side. If it's not, the answer is just no reactions. Okay, so the next one. I have a question
about that one.
Yes, go ahead.
You said tin is +2 or +4. Did you ever go over that? Because it said something about that on Chem 101, but I don't remember ever going over it being one of those two.
So the polyatomic ions have multiple charges. And on our periodic table, we don't have those multiple charges because I'm not making you memorize those multiple charges. If you take 210, which is general organic biochem, or 219, you will have to know those multiple charges. So for us, you wouldn't. So on this one, with Chem 101, it tells you it's +2 or +4. I should probably just take this one off because it would have worked if you used tin +4 also. It would have given you that one also. But
it doesn't tell you either way. Like you could see the equation right there. It doesn't tell you if it's 2 or 4.
Yeah, that's in chemistry. That's just something that we have to memorize. I'm not making you memorize it. That's why I said I'll probably take this one off Chem 101 because unless I start making you memorize charges, which is like 300 charges, you wouldn't have known that this is +2 or +4. That's why I just chose +2 for this one. And unfortunately, I've asked Chem 101 10 times, or more than 10 times, can I just please put a note in the problem saying tin is +2? And we don't have the capability to edit these. So I'll probably just go and remove this problem from Chem 101.
So nothing like that will appear where we're just going to have to know the charge of it that's not on our periodic table.
No, I would never do that on a Quizzer exam. No,
Okay.
Absolutely not.
Okay,
Yeah.
cool. Thank you.
Yeah, no problem. Okay. All right, I got a bunch of these dissociation questions. So we're going to do this. Dissociation means you put it in water and it comes apart, like salt. If you put salt in water, so if I have salt here and I put it in water, I have salt in water. Over time, the salt dissolves and I have a bunch of ions. That's what a dissociation is. It's an ionic compound in water that comes apart into ions, right? So if I put solid NaBr in water, then what happens to it? It's going to come apart into its ions. So this becomes Na plus and Br minus. Both of these are in, that doesn't look like an A, are in water. So that's what dissociation means. You put it in water and it comes apart into ionic compounds. The only time that it would be Nr, I'm gonna make one up. What if I put, so if I put like AgCl in water, this is an insoluble ionic compound. All chlorides, iodides, and bromides are soluble except silver, mercury, or lead, right? So it means it's a solid. So these are only going to be no reactions if this is an insoluble. So like, for example, if this was AgCl, I put solid AgCl here, over time, I would just have a bunch of AgCl sitting at the bottom, right? That's what dissociation means. And so the only time it's no reaction is if you look at your solubility table and it says insoluble. Okay, any more questions on dissociations? Because I've gotten a lot of these questions.
I have a question about BR. Sorry, how is the aqueous?
Say that one more time about Br and aqueous.
Yeah, on the table, I just don't see it on how I would know it's aqueous.
Because dissociation means, like, the dissociation means we're putting it in water. So that's what dissociation means. Like, what happens to an ionic compound when it comes apart? That's what the word dissociation means, comes apart in water.
Oh,
So
so
that's,
both of them,
sorry, go ahead.
sorry, both of them would be aqueous then if it has dissociation?
Yes. So what we would,
okay.
yeah, both of them. So this, we would have like just Na pluses and Br minuses just bouncing around in the water. So just be a bunch of these just bouncing around in the water as ions over time.
Thank you.
You're welcome.
Why doesn't bromine become diatomic because it's by itself?
Great question. Bromine, diatomic, is a molecular compound. This is an ion. In an ionic compound, Na is +1, Br is -1. This is a molecular compound, or an atom, which means it hasn't lost or gained any electrons. So there's no charge here, which means it's not an ion. The ion, again, is very different than the atom itself.
Okay, thank you.
Yes, great question. That's a great question. Okay, any other questions about dissociations? Because we've had a lot of these questions. I just want to make sure everyone's clear. Any others? Okay. Now this one, you can only use using the big solubility table. I pulled this off of Chem 101, which maybe you guys can tell me which solubility table you like better. So I'm going to use this one right now. I'm going to try and talk the chemistry faculty into using the nicer one.
Yours is better.
Oh, you like the other one better?
Yeah.
Oh, okay. Well, then we'll keep that one. I'm trying to get Chem 101 to like make it smaller and more tailored, but they don't listen to me. Okay, so ammonium sulfate and iron, I'm just making the bare bones here, iron chloride. So ammonium is a +1, sulfate's a -2. Iron, they told us, is a +2. Chloride is a -1. So we got to fix some stuff here, right? 2, 2. And it's a double displacement reaction. So ammonium stays first and Fe stays first. A little shorthand that I noticed some people do. Sometimes people won't do this part until they know the reaction actually occurs, because they're like, I'm not going to waste my time writing all this stuff down if I actually don't have to write it down. I mean, okay, that's fine. You don't have to do that. So the NH4 goes with the Cl and the Fe goes with the SO4. Okay, so I know this is aqueous. And then I'm going to use this one. So this one says soluble. So I'm looking for either iron or sulfate. So here's sulfate. Soluble again means AQ. And then exceptions would be solid. So sulfate is AQs except Ag, Sr, Caba, Ag. So according to this solubility table, this is also AQ. Okay, well that means my answer is no reaction. Because for a reaction to occur, something new has to form, right? So for a reaction to occur, something new has to form. Okay, so let's do one that actually occurs just really quick. Ki plus AgNO3. So when I do this, K stays first, Ag stays first, KNO3, AgI. I know this one's aqueous because I know all nitrates are soluble. I just memorized that one. So now I'm going to look for this one. So this is soluble except Ag, Hg, and Pb. So look at this one. According to this one, iodides, this is insoluble. So this would be a reaction that does occur. So for a double displacement reaction to occur, you have to have a new state. So this is a solid, these two are aqueous, so our answer to the first one is no reaction. Okay, and again, I didn't balance this. I did not balance anything here because I just wanted to see if there was a solid first. Then I would go through all the extra work. Okay, so I've gotten a lot of these. Let's do some complete ionic equations. I picked this one. Two people gave me this one. This is a rather difficult one. So let's do the rather difficult one. Okay. And the other one I got a lot was the bromine one. So we'll do that one too. What do we have here? Aluminum nitrate. And I'll do my balancing charges in just a second, and sodium hydroxide. Okay, so I balance my charges. Aluminum is +3, -1. So I need 3 of these, +1, -1. I'm just going to leave those charges here. I'm just going to leave them there for a minute. Now they have to switch. So Al now goes with OH, and Na goes with NO3. To balance this, right? +3, -1. So there's 3 of these, +1, -1. Okay, all nitrates are soluble. I know that one part. Okay, OHs. Sorry, hydroxides. All carbonates, phosphates are insoluble except ammonium and alkali metals. Nope, not an exception. This is our solid. Okay, so this is the molecular equation. I'm hoping that we're all pretty good with these so far. Okay, so this is our molecular equation. Our complete ionic equation, what we're doing is we're dissociating. Again, dissociating means we're taking them apart in water. So they're going to come apart into their ions. And so here's their ions. This is what they're going to come apart into. So they're going to break up. So if we put aluminum nitrate in water, it separates, the ions separate. So it's going to separate into aluminum 3+, plus there's 3 nitrates. 3 NO3 minus AQ plus, again, now this one is going to separate into Na plus AQ plus our OH, OH minus AQ. Now this is a solid, so I always suggest people put a box or a circle or highlight, something that kind of like makes us think, don't take the solid apart, right? The only thing that dissociates, or the only thing that comes apart in water, are only the AQs. Sorry, I forgot to put an AQ here and here. Only the AQs are going to come apart, right? And we know they're AQs because it says aqueous solution, right? So aqueous solution means dissolved in water. So this one stays together, but this one is going to come apart into its ions. NO3 minus. Well, I can see we made a mistake. Who can see the mistake? I make this mistake all the time. Okay, here's your hint. Look at the ones that we're going to cross off. Does anyone see it? Oh, I see. Someone typed in the chat. Yes. Anyone else? No. Okay, here it is. I have 3 nitrates on this side and only 1 nitrate on this side. What did I forget to do?
Do you put parentheses around the nitrate on the left side?
I did. See how there's 3 of them here, but there's only 1 over here. And look at our NAs worked out nicely.
You have to balance it?
Yeah, it's not balanced. I didn't balance the reaction. And so I'm going to do this in a different color just so you can see, because this happens a lot. There's so much going on with these questions that it actually happens quite a bit where you miss something, but it's okay as long as you catch it. So I caught it because I noticed that my nitrates didn't match. If I look here, look, I have 1 OH and I have 3 OHs. Something's fishy. In a complete ionic equation, it should work out perfectly. So watch what I'm going to do right now is I'm going to balance it. I'm going to put a 3 here, and then I'm going to show you how it fixes right here. So that means there's a 3 in front of my NAs and a 3 in front of my NO3s, right? But then my NAs don't work, so I have to put a 3 here, which makes a 3 here and a 3 here when I balanced it. Now, if I cross off the similar ones, oh, by the way, this is the complete ionic equation. So this is the answer for this question right here. Complete ionic means stop here. Where people go wrong on Chem 101 with this one, they forget the charges and they accidentally break this up. That's where the most issues happen. But okay, what I want to do now, I'm just in orange, I'm going to keep going to net ionic. So when you know your answers are correct, when everything works out perfectly at this point, you see how there's 3 nitrates and exactly 3 nitrates and 3 NAs and exactly 3 NAs? When it works out like that, you're probably doing the problem correctly. And then you just bring down everything else. Al, AQ, 3 plus, plus 3 OH minus AQ goes to Al, OH, 3 solid. So if you look at the balancing here, there's 1 Al, I'm just gonna do it like this, Al, OH, 1, 1, I did OH separately. I have to stop writing so quickly. OH, 3, 3. The balancing should work out perfectly. If it doesn't work out perfectly, that means something is wrong all the way up at the top. So it's usually up at the top where something's gone wrong. What's wrong? Usually balancing. If it's not balancing, you might have forgotten to balance the charges, right? Putting the 3 with the OHs. Those are usually the most common mistakes. This is the net ionic equation. This is what actually happened in the reaction. The spectators, those are the things we canceled out. So we canceled out the NAs and we canceled out the NO3s. These are our spectator ions. Okay. Question about this one. So go ahead.
You don't have to put the quantity of the spectator ions.
No, it's not wrong if you do, if you want to put the 3 on there, but it's not needed. Yeah, it's not needed. Okay. Let's try this one. I got this one so many times. At least this one, they wrote the problem for us, right? We didn't have to do any writing with this one at the beginning. Na3PO4, and it's telling us they're aqueous solutions. So I'm not going to go and look at my solubility table at all here. I'm just going to believe them. They said it's aqueous. Okay, I agree. It's aqueous. I'm just going to leave it at that. All right. So when you do this one, Ca stays first, and A stays first. The other 2 switch places. So the PO4 goes here, and the BR goes here. So if we put our charges here, they stay the same over here. And so this is Ca3, PO4, trying to make this as neat as I can, 2. All right, so if we have to have a new state, so one of these either has to be a solid, a gas, or a liquid. Otherwise, no reaction. So bromides are soluble except none of our exceptions. AQ, or you could have done this one too. All sodium is soluble, that can work too. Phosphates are down here. Phosphates are insoluble except ammonium and metal. That's not an exception, solid. All right, now let's not forget to balance this. Let's not forget to balance this time. I'm gonna leave those charges up there just because we're gonna use them in a second. So when we balance this, right, 2 here, right, 3 here, 6 here. And again, if you want to take the longer way to balance it, that's totally fine. But I'm just doing a little quicker now, but I can definitely do the longer way if anyone wants me to. Okay, make sure our balancing is right. This is, again, molecular equation. Molecular equation. This time they want to go all the way down to the net. They want us to go all the way to the bottom. Now we have to dissociate everything that's an AQ. Don't dissociate the solid. Solid stays together. Only the AQs. So this one comes apart. And this is why I left the ions here, so we remember what the ions are. And so your quizzes and well, you're not going to do these on your, no net ionics on your quiz, but on your exam, it is multiple choice. So if you want to just like leave these here, that's fine with me because it's going to be multiple choice anyway. This helps. So this is 3 Ca2 pluses, and I'm not going to write the AQ this time, but just notice all of these are AQ, okay? These are all AQs. Plus, there's 2 BRs. 2 BR minus plus 3 times 2 makes 6 NAs plus 2 phosphates don't take this one apart, leave it together. And remember, everything that doesn't have a state is AQ for this problem. 6 Na pluses and 6 Br minuses. This, again, this is the complete or total ionic, depending on what book you're reading. Okay, this question wants us to go all the way to the net. The net is like the simplest way we can go. So now we cross off everything that is the same on both sides. So, I made a mistake on that one. Okay, so everything that's the same on our both sides. So we see 6 NAs, 6 NAs, and I messed up our BRs here. 2 times 3 is 6 BRs. 6 BRs, 6 BRs. CA can't cancel, it's not exactly the same. PO4 can't cancel, it's not exactly the same. Those are the ones we're going to bring down. So 3 CA 2 plus, and I'm going to put the states in this one because it's smaller and neater, plus 2 PO4 3 minus AQ goes to CA PO4 2 solid. Did I write that right?
You forgot the 3 in CA.
I know, I'm like, there's something going wrong here. There it is. I'm like, something is very wrong. Thank you. That's why I'm like, there's just something not right. Thank you. Okay. Questions on this. This is the net ionic. If it asks us for the spectators, those are the ones that's what we, BR and NA. And again, these ions, it is important that you write the ions. The ions are very, very different than the elements. Very different. And oh, let me just write spectator. Okay, any questions on this one? I'm getting a lot of questions about these complete ionic equations. So I want to make sure that everyone is feeling better about them. Yes, better? Okay. This one's a little different, the next one. This one is a double displacement, but it's specifically asking about a neutralization reaction. So a neutralization reaction is just another kind of double displacement reaction. It's just a special double displacement, but really we don't treat it any different. So H stays first and BA stays first, and our anions just switch places. So this one goes HOH, this goes BaNO3. Got to do our charges, +1, -1, +2, -1, +1, -1, +2, -1. So we need 2 of these. Now, what makes this one different is, if you look, you'll see all nitrates are soluble, it's aqueous. This is water. Water is a pure liquid, right? So water is a pure liquid. And so when we write the balanced neutralization reaction, HOH becomes water. So I'm just going to put water up here so I don't have to rewrite the whole thing. And it's a liquid. So something new was formed. Water was formed. That's our new thing that was formed, right? And then we got balance it because it asks for a balanced reaction. So 2, 2. And if I take these charges off, this is what it should look like in the end. So neutralization, just remember, it just means double displacement. The only special part of it is it makes water. The HOH is water. And so we also will say acid plus a base makes a salt. That does not look like an A. Salt and water. And remember, salt is just any ionic compound. And so this is a neutralization, just an extra special double displacement, but really the rules don't change. The only thing that's new is you form water instead of a solid. Okay, this was another question I got a few times today. What are the products of this reaction? Okay, so whenever you have a hydrocarbon, which just means hydrogens and carbons, and sometimes we throw some oxygens in there too, it's always a combustion. So combustion always makes CO2 and water. So C3H7OH, whenever we burn anything, we can only burn things with oxygen, right? If you have a candle and you put a top on the candle goes out because there's no oxygen, right? So whenever it says anything burns, How are we talking about a combustion reaction? The products of a combustion reaction are always the same. It's always CO2 plus water, right? So CO2 plus water. Combustion reaction, so you could have CaH18 plus oxygen. Products, CO2 plus water. You could have C2, this doesn't exist, O4H9. Products, CO2 plus water. So combustion always makes CO2 plus water. So lock that one away in our brains. Okay, now balancing these is no fun. Okay, so this is a net ionic equation. This one's a regular one. And there's a couple others. I got this one a few times today. So let's do this one. And then there's another dissociation question that I've gotten asked like 4 times today I want to do. Okay, again, net ionic equation, pretty much the same as we just did. BaCl2. It says they're aqueous, I'm going to believe them aqueous, plus ZnSO4 says it's aqueous, I believe them. Ba plus Zn. So it's going to be Ba and SO4 and Zn and Cl. So if we do our charges, +2 - 1, +2 - 2, +2 - 2, +2 - 1, Cl2. Okay. I know that chlorides are soluble. I've looked at it enough. Sulfates. They're sulfates. They are soluble, so they are AQ, except barium, strontium, lead. That's an exception. This is a solid. Okay, I have to balance it. It's balanced. Yay. Okay, so we're good with this one. Now we have to take it apart. And again, I'm not going to write the AQs. Everything's AQ here except for the solid. Oops. Try that one more time. This stays together. Everything else is going to come apart. We have 1 Ba, it's charged +2, 2 Cls, plus Zn +2, plus SO4 -2 goes to BaSO4 solid plus Zn +2 plus 2 Cl minus. And again, they're all AQs except for the ones, except for this one. All right, cross everything out, that's exactly the same. Well, Cl is exactly the same. Cl is exactly the same. Zn is the same. Zn is the same. So this is what's different. So this is Ba AQ plus SO4 2 minus AQ goes to BaSO4 solid. This is our net ionic equation. So if you have a question that's asking for net ionic, you kind of have to, it's a long process, right? Because you have to go through all of it. They just take a little bit longer than any other equations that we do. All right, any questions on this one?
I do. I have a question about the state for ZnCl2. Can you tell me again why it's aqueous?
Sure. So I just looked here at the solubility table. And this one says all chlorides, bromides, and iodides are soluble, except silver, mercury, and lead. This is neither silver, mercury, or lead, so it means that it is indeed aqueous. Yes. So again, soluble means AQ.
I have a question regarding the solubility rules.
Mhm.
When you see chlorates, does that mean the same thing as chlorides?
It does not.
So what's the rule for chlorates? Because I don't see them on here.
That would be a bigger solubility table. You couldn't do chlorates with this one.
Okay.
Yeah, so you won't, the only ones you're going to see are the ones that are on here. So I think if you look at like the Chem 101, right? See, it's got chromates on here and sulfites on here, and there's perchlorate. It's got a lot more. We're not using those. The only ones that you're going to have to, this is the one we just did, right? Oops. The only ones you'll see are on here. So the only polyatomics you're going to see in double displacements are in these. Phosphates, hydroxides, sulfates, ammonium.
Okay. So
Yeah.
some of the questions are on 101 on my quiz or exam.
None of, yeah, you're only going to see these
Okay.
on your quiz and exam. Yeah, Chem 101 just uses more. There's only so many reactions we can do with these. So that's why Chem 101 has a much bigger solubility table. Yes. Okay, any more questions on this one? So someone had a good question. It was a dissociation question. And I've actually got this one a couple of times about ALBR3 dissociation. So I just want to go over that one just really quickly. And so it asked about the dissociation of ALBR and then, why that's not writing, 3 solid. So again, this is like putting, think of it as salt. Salt is a solid. When you put salt in water, it comes apart. ALBR3 is a solid. When we put it in water, does it come apart? I'm pretty sure it does. All chlorides, bromides, and iodides are soluble, except that is none of our exceptions. So when it comes apart into its ions. This is a +3, this is a -1. So it comes apart into Al3 plus. AQ means now it's an ion floating around in water. +3 Br minus AQs. And again, these AQs mean they're in water, right? They're ions floating around in water. Ions in water. So I got that one a couple times today. Okay. So let's do one more net ionic equation that we got. Okay. Oh, this was just a balanced chemical reaction. A balanced chemical reaction on this. So potassium is K, phosphate, PO4, 3 minus, reacts with nickel 2, reacts with, that's the plus, nickel +2, bromide, Br, and I'll worry about the balancing charges in just a second. To produce, that's our arrow, solid nickel +2 phosphate, and aqueous potassium bromide. And this one says this is going to be a solid, and this one is an aqueous. And it said this one was aqueous, and it also said this one was aqueous. All right, so now I got to fix these. 3, 2. I don't think I left myself enough room to do this one. See how neat I can do this. 2, and this one's good. All right, so we balance all our charges. Now I gotta balance the reaction, right? So if we balance this, 3 nickels. I'm just gonna erase these. 3 nickels, 3 nickels. Well, that just messed up my bromines, my bromides. There's 6 of those, so I'm gonna put 6 of those. I don't have 6 Ks, but I only have 3 Ks, so I'm gonna put 2 here. And then I think that just worked. Yep, there we go. That's our balanced molecular equation here. So it's just following those steps, right? Find the rule on the sheet. We know this one, we didn't have to follow the rule on the sheet, balance the charges, and then balance the reactions, write the states. All right, any questions on this one? No? Good on this one? Okay, so we've done a ton of net ionics. We could do and complete ionics. Do you want to do another net ionic or complete ionic, or are we good with those? Does anybody want to do another one? Because we can if you want.
I had one that I thought I completed and I balanced, and then it still said it was incorrect.
Do you remember which one it was?
Yeah, let me.
You can also do this one, FeCl3 plus NaOH. That's one. So this question here asks for spectator. So Brett, while you're looking for that,
Okay.
let's do this one real fast. This one asks for the spectator ion. So I'm going to go kind of quick on this one because we've done this a few times now. Just stretching my hands. So for this one, and when I go quick, sometimes I make mistakes. So please watch closely and tell me what I'm doing wrong at any time. Here's OH, and here's Cl, right? This is +3 - 1. I'm going to leave these charges up here because I feel like that might help. So we need 3 of these, and then we have to balance it. Balance it. Should be balanced, right? So this is AQ, this is AQ. I know this one's AQ. FeOH, all hydroxides are insoluble except ammonium and alkali. So insoluble means that FeOH is insoluble, which means it is a solid. So this one is going to stay together. Everything else is going to fall apart. So it's all going to come apart. So we have Fe, 3 plus 3 Cl minuses plus 3 Na pluses plus 3 OH minuses makes, don't take this apart, OH 3 solid plus 3 Na pluses plus 3 Cl minuses. So I just dissociated everything. Remember, these are all AQs, I just didn't write the AQs. Then we cross off everything that is the same. What we just crossed off, those are the spectators, right? So our spectator ions here would be Na plus and Cl minus, right? If we want to do our net ionic, we just bring the rest down. Fe 3 plus, and again, these are AQs plus 3 OH minus. AQ goes to Fe OH 3 solid. This is the net. On that one, but you can see it's kind of a system that you just kind of again and again and again. It says my internet's unstable, so I'm sorry if you can't hear me. Too many people on the internet in my house. Any questions on this one? No? Okay, Brett, do you have that question that you were stuck on?
No, I went back and I think I had ended up figuring it out.
Figured it out. Okay, any other questions for today? I want to let everyone know that tomorrow I have to leave at 7 because it's my daughter's 16th birthday and we're taking her out to dinner to her favorite Indian restaurant. So just letting you know. But today I can stay as long as you want. So any other questions that you have on here? Aluminum nitrate and potassium iodide. I'm just getting to one where I can erase everything really quick. So someone had a question about aluminum nitrate. So aluminum nitrate and potassium iodide. And so +3 - 1 + 1 - 1. So we need 3 of these. And it's a double displacement, obviously. So Al plus K, and then they switch ALI, that just looks weird, and KNO3. This one's no reaction. That's why it's probably giving you trouble. So this is AQ, and this one's AQ. How do I know this is no reaction? I know nitrates, all nitrates are soluble. Let's go to our solubility table. Let's go to our solubility table. So I'm looking for ALI. Let me just fix the charge. I can't help it. It's driving me crazy. Right? +3 - 1 + 1 - 1. So ALI3. All chlorides, bromides, and iodides are soluble except silver, mercury, and lead. This is not an exception. This is an AQ. Because this is an AQ, the answer is no reaction. Yes, so the answer is NR for this one. So that would be our answer, NR, we would just do. So again, that solubility table, that's really gonna help us with that. Okay, Regina, is that better? Helpful?
Yeah, I missed that. I sometimes miss those. If it were able to go on with it for writing the net ionic, would it be Al3 plus, and then would it be NO3, and then would there be, well, actually, would it be 3 NO3?
Yeah, so we got to balance it first. So you have 3 and 3. So what happens if you try to do the net ionic? Watch what happens when we try to do this. +3 + 3 NO3 minus this +3 Ks. And these are all AQs, right? Plus 3 I minuses goes to AL +3 plus 3 I minuses plus 3K plus 3 NO3 minuses. Then you cross off everything that's the same. Aluminum, aluminum, 3 nitrates, 3 nitrates, 3 Ks, 3 Ks, 3 Is, 3 Is. And crossed off everything. So if that happens, they must have all been aqueous up here. So make sure you check the solubility table for these states. Very, very important that we check our solubility table. Does that answer your question about what the complete ionic would look like?
Yeah, it just sometimes throws me off whenever I drop it down with the charges and then balancing it on how to write it sometimes. But
yeah, like that I3 becomes 3I.
Yeah.
Yeah, so and we'll learn this later. So what this is 1 aluminum, and it has like three I's like attached to it. Not like this, it's not actually gonna look like this, but for our purposes, I'm gonna use that. And so that's what this is. So when you separate them, you have 1 aluminum and 3 I's. So that's where the 1 aluminum and the 3 I's come from. Does that make sense? When we do bonding metaphor, it'll make more sense. But yeah, so these subscripts end up going in the front. Yes. Okay, any other questions?
I think I found the one that I was having an issue with.
Oh, go ahead.
Do you want us to read it to you?
Yes, go ahead.
It's going to be iron to nitrate, NO3.
Okay.
Aqueous plus potassium hydroxide aqueous. And then it says complete the balanced molecular chemical equation.
Okay, so 2, right? We have to balance that. Was it iron 2, correct?
Yeah.
Okay. So again, another double displacement. And so we switch this. So this is going to be OH, and this is going to be NO3. So if it was a +2, it's going to stay a +2. So we have to put a 2 here. And then I'm just going to erase these charges because we don't need them. I know this one's aqueous. This one's a solid. Because if we look at our solubility table, all hydroxides are insoluble except ammonium and the alkali metals. So where did this just go? This is neither ammonium nor an alkali metal, so it's going to be a solid. And then we have to balance it. So we can kind of pick nitrate. I'll do nitrate, 2 nitrates. And I got to fix my Ks. And that works out. Great.
That's what I wrote, and it says your formula FeOH2.
This one. Did you write aqueous or solid?
I wrote solid. It says your formula FeOH2 appears to have a deficient number of oxygen atoms in it. Is it because I didn't put parentheses around the OH?
Yeah, you definitely need parentheses.
Okay.
Because if you don't put parentheses, then it says you have two
H's
hydrogens and one O.
Okay, that makes sense.
Yeah. Yeah.
Okay, perfect.
Yeah.
Thank you.
I was like, well, how do you have a deficient number of oxygens?
That's what when I kept looking over it, I kept seeing OH as 2 of each, but it's because I forgot the parentheses.
The parentheses, yeah. Those parentheses matter, yes.
Okay, thank you.
You're welcome. Any other questions that anybody has? I think I've answered all of them in the chat. Going through them. Okay, any other questions for today?
I have a question.
Go ahead.
Can you do number 16? Oh, I'll send it.
Yeah, because my 15 is different than your 15.
No, 16. I could send it.
Okay, perfect. Do you know what it starts with? Because I can look it up really fast too.
H2SO4 plus PbOH.
H2SO4 plus, what was it? Oh, I found it, PbOH4?
Yes.
OH4, and it says balance the following equation, right?
Yeah.
So balance this one, and so it goes to PbSO4 2 solid plus water liquid, and this is aqueous, and this is a solid. And so it says balance this. Okay.
Yeah.
So a couple of different things we can do here. I would not touch the O's. I would look at where's my H's. Can I fix my H's on this one? So you see how there's like O's everywhere? Just don't touch the O's. That's what I would suggest. Try on the H's. So there's 4 H's. Oops. 4 H's here. And 2 here, so I would try this first because we can't keep our polyatomic ions together. So that fixes our H's, but now we only have 2 O's over here. How about our S's? I'm gonna go and try our S's because this isn't leading me anywhere right now. So do you see how there's 2 S's right here? I'm gonna fix an S. So if I put a 2 here, maybe that will help. And you can do this the long way or the short way. The long way isn't super helpful here. And let me just show you why. I'm gonna try it the long way because I know people like that. So we have H, S, O, and PB. So 2, 2, 1, 2, 4, 8 O's, 8, 9 O's. PB1, PB1. See, this is why I said I'm going to stay away from my O's. So the first thing I thought, I'm going to try the H's.
What I did is I did SO4 as one of them instead of S and O separately.
Yeah, we could totally do that one. So we could do that one. So it's 1 and 2. So the H's, that's what I tried first. But see how now it doesn't. Do you see how now, like, I changed my O's, but I,
Well, You need the O as well by itself.
Yeah, so you'd have to do O you'd have to do O separately by yourself, which you could do. So this one you treat as 1 and this one you treat as 1, right? But then you can't treat this one as 1. So the long way is kind of, it works, but it has some issues over here. So if we do it like this with the O's and the S, what I would do here, I'm just gonna change. I would start with the S's. Because I can see here, there's 1 here. If I multiply that 2, I would start here with this one, just because I think it will work better. And so if we try that one, now we have 4 H's, 2 SO4s, 4 H's on this side, 2 SO4s. So we're good here. Check out our PBs, 1 PB, 1 PB. Check out our O's with our H, 4 O's.
Isn't it 8 H's?
Am I reading? Where's our 8?
You got 2 and the 2 H2s, and then you have the 4 on the OH.
Yeah, missed that one. 8 H's. Yeah, so then that means we have to fix this one. 4 H's. Eight. And then 4 O's. So this one's a little bit of trial and error on this one. It's a difficult one to balance. Yeah, so there's a couple different ways. So you can split it up like that. You can split it up like this. You can just do trial and error by looking at them. There's a couple different ways you can do it, but it's a tricky balancing one. But whatever works best for your brain, that's what I would go with.